Welcome to Nitoria. It's lovely to have you here tonight. Wherever you are right now, whatever has brought you here, I'm glad you came. Maybe you're lying in bed with the lights already low, the blanket pulled up, just the way you like it. Maybe you're on a couch somewhere, or a train, or in a quiet room with one small lamp still glowing in the corner. Maybe it's late, or maybe it's the strange middle of the afternoon, and you just need somewhere soft to rest your mind for a while. However you got here, settle in. There's no rush. There's nowhere else you need to be. And before we begin our journey for the night, I'd love to know, where in the world are you listening from? What time is it in your little corner of the world right now? Leave it in the comments if you feel like it. I always like imagining the map of us, all these quiet rooms scattered across the night. All of us drifting off to the same slow voice. And if you enjoy these slow journeys and want more of them, a gentle like and a subscribe really does help this sleepy little channel keep going. Small creators like me genuinely rely on it. And to those of you already subscribed, already part of Nitoria, thank you, truly. You're the reason these nights exist. Now, a small warning, said with a smile. Tonight's subject is one of the strangest, grandest, most beautiful things in all of science, and I'll try my very best not to make it so interesting that it keeps you awake. But if it does, well, at least you'll have learned something lovely on the way. A fair trade, I think. So here's the plan. We're going to take a long, slow walk tonight. We're going to wander all the way from the smallest, strangest objects in the universe to the very last things that will ever exist when time itself is running out. We'll move gently, one idea at a time, with plenty of room to breathe. You don't have to follow every step. You don't have to remember any of it. If you drift off somewhere in the middle, that's perfectly fine. The universe will still be here, and so will all these ideas waiting patiently for the next time. There's no test at the end. There's only the journey, and the rest you're hopefully sinking into right now. Let's begin, shall we? I want to start with something that sounds at first like a contradiction. I want you to imagine the single brightest object in the entire universe, not a star, not an exploding star, not a whole galaxy full of stars. The brightest single object we have ever found anywhere in all of creation. And here is the strange part, the part I want to gently turn over and over in your mind tonight like a smooth stone in your palm. That brightest object, that blazing, roaring lighthouse of light, is powered at its very heart by the darkest kind of thing the universe has ever made. A black hole. Let me tell you about it, because it's almost too much to believe. In 2024, astronomers with the European Southern Observatory announced that they had confirmed the most luminous object ever observed in the universe. Its name isn't poetic, I'm afraid. It's called J0529-4351, just a string of numbers from its position in the sky. But what it is breathtaking. It is a quasar, and we'll talk in a moment about exactly what that word means. And it shines with roughly 500 trillion times the brightness of our sun. Sit with that number for a moment, because it's so large it almost slides right off the mind. Our sun is already so bright that you cannot look at it for even an instant without hurting your eyes. It pours out enough light to warm an entire world from 93 million miles away. Now take that and multiply it not by 100, not by 1,000,000, but by 500 trillion, a 5 with 14 zeros after it. There is nothing in your daily life to compare it to. It is brighter than entire galaxies. It outshines hundreds of billions of stars all at once, from a region of space smaller than our own solar system. And the engine driving all of that light? At the very center of it, doing the actual work, is a black hole. A black hole so hungry that it is devouring every single day about 1 sun's worth of material. Not in a year, not in a lifetime, in a day. Imagine our entire sun, that vast, fiery sphere, being swallowed in 24 hours, and then another one tomorrow, and another the day after that. That is the appetite of this thing. The material it's feeding on doesn't fall straight in. It swirls. It piles up into an enormous flattened ring of gas and dust spiraling inward, like water circling a drain, but on a scale that defies imagination. That ring, or we call it an accretion disk, and we'll come back to that lovely word, is about 7 light years across. 7 light years. Light, the fastest thing there is, would take 7 years just to cross from one side of it to the other. Our nearest neighboring star is only a little farther than that. The whole glowing disk feeding this one black hole is nearly as wide as the gap between the Sun and the next star over. And as that material spirals inward, it grinds against itself, it compresses, it heats up to unimaginable temperatures, millions of degrees, and in its dying fall it screams out light across the whole spectrum. That is where the 500 trillion suns of brightness come from. Not from the black hole itself. The black hole gives off no light at all. But from the doomed, brilliant, infalling matter on its way down. So here is the first gentle knot I'd like to loosen tonight, and it's the first of 3 big surprises this whole journey is built around. We call them black holes, but the brightest object in the universe is one. And that already tells you that almost everything the name suggests is, in some quiet way, wrong. It is not really a hole, as we'll see, and it is very far from being entirely black. Hold on to that thread, we'll pull on it slowly all night long. But before we go any deeper, let's talk about the name itself, because there's a small, very human story tucked inside it that almost nobody knows. You've probably heard, somewhere along the way, that the term black hole was invented by a famous American physicist named John Archibald Wheeler. It's one of those facts that gets repeated so often it just becomes part of the furniture. And it isn't quite true. Wheeler certainly made the name famous. He used it in a lecture in 1967, and after that it stuck, and it spread, and it became the only name anyone ever used. But the phrase was already floating around before that. It appears earlier in reporting from a science conference in 1963 and then in print in 1964 in an article written by a science journalist named Anne Ewing. She deserves a little of the credit that history quietly handed to someone else. And do you know what these objects were called before that, in the stiff, careful language of the physicists who first described them? They were called gravitationally, completely collapsed objects. Say that out loud, slowly. Gravitationally, completely collapsed objects. You can see, can't you, why a shorter name was needed? You can see why black hole, whoever first whispered it, swept the old clunky phrase away almost overnight. There's something about the right name. It makes a thing feel real. It gives the imagination something to hold. So, we have a name. Now let's ask the gentlest, most fundamental question of the night. Where do these things actually come from? How does the universe make one? For the most common kind, the answer begins with a dying star. Stars seem permanent to us. They've hung in the same patterns over our ancestors' heads for all of human history, but a star is not a solid object and it is not eternal. A star is a long, slow, balanced battle. On one side you have gravity, forever trying to crush the star inward, pulling all that enormous mass down toward the center. On the other side you have the heat and pressure of nuclear fusion in the star's core, where atoms are being fused together and pouring out energy, pushing outward, holding the whole thing up. For most of a star's life, those two forces are beautifully matched. The crushing in and the pushing out cancel each other, and the star sits there, steady, shining, for millions or billions of years. But fuel runs out, it always does, and when a truly massive star, one much heavier than our sun, somewhere above 20 or 25 times the Sun's mass, finally burns through its nuclear fuel, the pushing out stops. The fire at the center goes quiet. And in that instant, gravity, which has been patiently waiting all along, finally wins. The core collapses. It falls in on itself with astonishing speed and force. And here's where it gets interesting, because not every collapse goes all the way. Sometimes the collapse halts and leaves behind an incredibly dense object, a kind of cosmic ember. But if the collapsing core is heavy enough, if what remains is more than a certain critical amount, then no known force in nature can stop it. Nothing can hold it up. It just keeps falling inward, smaller and smaller, and denser, with nothing left to push back. That critical amount has a name, and it's a bit of a mouthful, but I'll give it to you, and then we'll set it gently aside. It's called the Tolman-Oppenheimer-Volkoff limit, named after the three physicists who worked it out. You can just call it the TOV limit if you like. It sits somewhere around 2 and a bit to nearly 3 times the mass of our Sun. Below that limit, the collapse can be stopped, and you get that dense ember I mentioned. Above it, and there's no stopping it. The core falls and falls, and a black hole is born. Now, you might reasonably wonder whether this is all just theory, whether maybe nature has some trick up its sleeve to halt the collapse before it gets that far, some safety mechanism we just haven't found. And for a long time, some of the greatest minds in physics quietly hoped exactly that. They suspected the whole runaway collapse might just be a mathematical illusion, something that only happened in the tidy, perfect, symmetrical situations physicists like to put in their equations, and would never actually happen in the messy, lopsided real world. It took a brilliant mathematician named Roger Penrose to settle the question. In 1965, Penrose proved something profound. He showed, with the cold certainty of mathematics, that the collapse to a black hole isn't an artifact of perfect symmetry at all. It's robust, it's inevitable. Take a real, lumpy, imperfect, spinning, wobbling, massive star, let gravity win, and the math says a black hole forms. Every time, unavoidably. There's no trick, no escape hatch, no hidden safety mechanism. The universe really does build these things. It was such an important result that 55 years later, in 2020, Roger Penrose was awarded the Nobel Prize in Physics for it. For proving that black holes aren't just allowed by Einstein's theory of gravity, they're demanded by it. A consequence so deep and so certain that the universe could hardly avoid making them. And that name, Einstein, brings us to the very foundation of all of this, and to one of the most quietly moving little stories in the whole history of science. So let's slow right down here, because this part deserves it. In 1915, Albert Einstein gave the world his theory of general relativity. It's one of the great achievements of the human mind, and at its heart is an idea that's strange and beautiful and worth dwelling on for a moment. So let me try to give it to you plainly. We tend to think of gravity as a force, a kind of invisible rope pulling things together. An apple falls because the Earth is tugging on it. The moon circles us because we're tugging on it. That's how it feels, and for everyday life it works perfectly well. But Einstein saw something deeper. He realized that gravity isn't really a pull at all. It's a shape, mass. Anything with weight, anything made of matter, bends the very fabric of space and time around it. The more mass, the deeper the bend. Here's an image to hold while you drift. Imagine a large, soft, stretchy sheet pulled tight like a trampoline. Now set a heavy bowling ball in the middle. The sheet sags, doesn't it? It curves down into a dip around the ball, and if you roll a little marble across that sheet, it doesn't travel in a straight line anymore. It curves. It might even circle round and round the dip before spiraling in. Nothing is pulling the marble toward the bowling ball with an invisible rope. The marble is simply following the shape of the bent sheet beneath it. That, more or less, is Einstein's gravity. The sun isn't tugging on the Earth with a rope. The Sun is so massive that it puts a great dip in the fabric of space and time, and the Earth, like that marble, is simply rolling along the curve, going round and round in the dip we call its orbit. Space tells matter how to move. Matter tells space how to bend. A simple, gorgeous idea that completely rewrote our understanding of the cosmos. Now, Einstein wrote down the equations for all of this, and they are famously difficult. Even Einstein himself didn't immediately solve them for any specific real situation. And here is where our little human story comes in. There was a German physicist and astronomer named Karl Schwarzschild. And in 1916, just months after Einstein published his theory, Schwarzschild did something remarkable. He found an exact solution to Einstein's equations. He worked out precisely how space and time bend around a single concentrated mass, a clean and complete answer to a problem people expected would take years to crack. And he did it under conditions you can scarcely imagine, because in 1916 the First World War was tearing across Europe, and Karl Schwarzschild, a middle-aged man, a respected scientist, had volunteered and gone to serve. He worked out his solution to the deepest equations in physics while stationed on the Russian front. Picture that for a moment. The mud, the cold, the noise and fear of war all around him, and this man, in the middle of it, quietly bending his mind around the bending of space-time itself. Doing some of the most beautiful mathematics ever done in one of the ugliest places a person could be. And the saddest part, while he was at the front, Schwarzschild contracted a painful illness, a disease of the skin, and it took his life that same year. In 1916, he lived just long enough to send his solution to Einstein, who presented it to the world on his behalf. He never lived to see what his equations truly described. He never knew that buried inside his neat little solution was the mathematical fingerprint of a black hole, decades before anyone would even use that name. He gave us the map of these objects and then was gone almost at once, like a man who lights a lamp in a dark room and steps away before the light fully fills it. His name lives on in two of the most important ideas about black holes, and we'll meet them both. The first is the Schwarzschild radius, and to understand it, we need to talk slowly and gently about the most famous feature of a black hole, its edge. The point of no return, the thing called the event horizon. So what is the event horizon? Let me build it up carefully because there's a lovely logic to it. Remember that a black hole is a place where so much mass has been crushed into so small a space that the bending of space-time around it becomes extreme. Not a gentle dip like the sun makes, but a deep, steep, plunging well. And the closer you get to the center, the steeper the well and the harder it is to climb back out, meaning the faster you'd have to move to escape. Now there's a speed limit built into our universe, and it's the speed of light. Nothing can travel faster than light. Light itself is the fastest messenger there is. And as you fall closer and closer toward the heart of a black hole, there comes a particular distance, a particular boundary, where the escape becomes so steep that you would need to travel faster than light just to climb back out. And since nothing can do that, not a spaceship, not a beam of light, not anything at all, that boundary becomes a one-way door. Cross it, and you can never, ever come back. Not because something is holding you, simply because every possible path forward, even for light, now leads deeper in. That boundary is the event horizon. It is the edge of the black hole, the surface of no return. And the distance from the center out to that boundary, the size of the event horizon, is exactly what Karl Schwarzschild calculated. We call it the Schwarzschild radius in his honor. And here is something genuinely lovely about it, something simple and clean amid all this strangeness. The Schwarzschild radius depends on just one thing: how much mass the black hole has. That's it. Double the mass, and you double the size of the event horizon. The relationship is beautifully direct. More mass bigger horizon, less mass, smaller horizon. There's even a tidy little equation for it, but you don't need the equation tonight. You only need the idea the size of a black hole is set entirely by its weight, and this leads to a thought that I find genuinely delightful, the kind of thing that makes you smile in the dark. You can ask, what would the event horizon be, the Schwarzschild radius, for any object at all? Because Schwarzschild's formula doesn't only apply to dead stars, it applies to anything. You just have to imagine crushing that thing down small enough. Take our sun. If you took the entire sun, all of that mass, and crushed it down until it became a black hole, how big would its event horizon be? The answer is about 3 kilometers across in radius. Roughly the size of a small town. Our enormous blazing sun, the thing that's nearly 900,000 miles wide, would have an event horizon you could walk across in an afternoon, if walking across such a thing were remotely possible, which of course it is not. And now take something smaller. Take the Earth, the whole planet beneath your feet, all of its mountains and oceans and continents and molten core. What would it take to turn the Earth into a black hole? You would have to crush the entire planet, every grain of it, down into a sphere about 9 millimeters across. 9 millimeters, that's the size of a small marble. A child's marble you could close your hand around. The entire Earth, every ocean, every mountain, every living thing, all of human history, squeezed down until it would sit, weightless looking, in the palm of your hand, and yet so dense that not even light could climb back out of it. That's how extreme a black hole is. It isn't that black holes are made of some special exotic stuff. It's that ordinary stuff, a star, a planet, has been squeezed so impossibly tight that the very shape of space folds shut around it. The mass stays the same. It's the smallness that does it, the crushing, the collapse. And here's a gentle reassurance, because people sometimes get this wrong and it worries them a little. A black hole does not go around the universe sucking things in like a cosmic vacuum cleaner. That's not how gravity works, even here. If you took our sun and magically replaced it, this very instant, with a black hole of exactly the same mass, a 3-kilometer black hole sitting where the sun used to be, the Earth would not get pulled in. The Earth would simply keep orbiting exactly as it does now, in exactly the same path, completely undisturbed. It would get very cold and very dark, of course, with no sunlight, but it would not be swallowed, because the mass would be unchanged, and so the dip in space-time far out where the Earth orbits would be unchanged too. Gravity outside a black hole behaves perfectly normally. You only get into trouble if you go very, very close, closer than anything ever orbits, right down toward that point of no return edge. So a black hole is not a hungry mouth roaming the cosmos. It's just a place where a great deal of mass has been packed into a very small space, bending the world around it into a well so deep that, past a certain edge, there is no climbing back out. And that edge, that quiet, invisible boundary we call the event horizon, that's where one of the strangest and most beautiful surprises of this whole journey is waiting. Because you might imagine that crossing it would be violent, dramatic, a wall of something, a moment you'd feel in every bone. You might imagine you'd know in the instant you crossed that you had passed the point of no return. But the truth is far stranger and far quieter than that. The truth is that for a large enough black hole, you could cross that line, the most absolute boundary in all of physics, the edge past which nothing ever returns, and feel absolutely nothing at all, no wall, no jolt, no sign, no sensation whatsoever. You would drift across the most important threshold in the universe without the slightest idea that you had done it. And to understand how that could possibly be true, how the point of no return could feel like nothing at all, we need to look very closely at what the event horizon really is, and what it isn't. Because despite the name we've given these things, a black hole is not, in the way you're picturing it, a hole. There is nothing to fall through, there is no surface to strike, and the closer we look at that single strange fact, the stranger and the more wonderful it's going to become. Welcome to Nightauria. It's lovely to have you here wherever you are tonight. Maybe you're under a heavy blanket with just one lamp still glowing in the corner. Maybe you're on a train or a couch with a cup of something warm going cold beside you. Wherever you are, settle in. There's nothing you need to do here but breathe slowly and let the words drift over you. And if you enjoy these slow journeys into the night, a quiet like and subscribe really does help this sleepy little channel keep going. Small creators like me rely on your kindness more than you'd think. And to those of you already here, already part of this, thank you, truly. So before we begin, tell me, where in the world are you watching from tonight? What time is it in your corner of the night? Now, and here's my one promise to you. We're going to move slowly. There's no need to grasp every detail, no need to follow every twist. If you drift off somewhere in the middle, that's perfectly fine. The ideas will still be here, patient and waiting, the next time you come back. I'll try not to make this so interesting it keeps you awake. Though if it does, well, at least you'll have learned something. A fair trade, I think. So, let me show you something before we go any deeper into that strange, quiet edge. There is right now an object in the universe so bright it's almost impossible to hold in your mind. It shines with the light of 500 trillion suns. Not 500, not 500,000, 500 trillion. And here's the part that should make you pause, even as you're getting sleepy. That blazing, impossible brightness, the brightest sustained thing we have ever found anywhere in all of creation, is powered by the darkest object that exists. It's a quasar. Astronomers gave it a name like a license plate, J0529-4351. They announced it in 2024, a team working with the European Southern Observatory, led by a researcher named Christian Wolff. And at the heart of it sits a supermassive black hole, feeding, eating. And the amount it eats is hard to picture too. It swallows roughly one sun's worth of material every single day. A whole star gone every day, the way you or I might finish a small cup of tea. As all that matter spirals inward, it doesn't just slip quietly over the edge, it piles up. It crowds together into a vast, flattened ring spinning around the black hole, what we call an accretion disk. And in this case, that disk is about 7 light years across. 7 light years. Light, the fastest thing there is, would take 7 years just to cross it. All that matter, squeezed and grinding against itself, heats up to temperatures so extreme it screams across the whole spectrum of light. That's where the brightness comes from, not the black hole. The black hole gives off nothing. It's the doomed material glowing in its last moments before it crosses the edge that lights up the cosmos. So you see, a black hole is not, in any simple sense, black. The darkest thing we know wears the brightest crown in the universe. Hold that thought gently. We'll come back to it. But for now, let's go back. Way back. Because before we understood any of this, before we had pictures, before we had a name, we had only a strange piece of mathematics and a very human story. It begins with a name, oddly enough. You've probably heard that the term black hole was coined by the physicist John Wheeler. It's a tidy story, often repeated. And it isn't quite true. Wheeler certainly made the phrase famous. He used it in a lecture in 1967, and after that it stuck to these objects forever. But the words were already drifting around before he reached for them. They appear in reporting from a conference in 1963 and then in an article in 1964 by a science journalist named Anne Ewing. Wheeler simply liked it because the name physicists had been using until then was, frankly, a mouthful. They'd been calling these things gravitationally completely collapsed objects. You can understand why black hole caught on instead. But the idea itself is older still, and it was born from a quieter, sadder story. In 1915, Albert Einstein gave the world his theory of general relativity, a new way of seeing gravity, not as a force pulling on things, but as the bending of space and time itself by anything that has mass. The equations were beautiful, and they were difficult. Einstein himself doubted anyone would find an exact solution to them soon, but within months, someone did. His name was Karl Schwarzschild, and here is the part that stays with me. He worked out his solution in 1916, not in a comfortable study, not at a chalkboard in some quiet university hall. He did it while serving as a soldier in the First World War, on the Russian front, in the cold, and the noise and the danger of it. He sent his work back to Einstein from the trenches, and only months later, he fell ill and died. He never lived to see what his equations truly described, that buried inside them was the first real hint of these impossible objects we're talking about tonight. So how does one of these things actually come to be? Where do black holes come from? For most of them, the answer is simple and a little sorrowful. They come from the death of stars. A star spends its long life in a kind of gentle balance. Deep in its core, it's fusing light elements into heavier ones, and that fusion pushes outward, a constant warm pressure holding the star up against its own enormous weight. Gravity pulls in, fusion pushes out, and for millions or billions of years, the two of them hold hands and keep the star steady and shining. But the fuel runs out, it always does. And when a very massive star, while weighing more than roughly 20 or 25 times the mass of our Sun, finally burns through the last of it, that outward push simply stops. There's nothing left holding the core up, and so it collapses inward all at once. Now, ordinarily, something would catch it. Even after a star dies, the matter left behind can push back in stranger, quieter ways, holding the collapse at bay. That's how we get neutron stars, incredibly dense remnants, but stable. But there's a limit to how much even that can hold. Physicists call it the Tolman-Oppenheimer-Volkoff limit, a long name for a simple idea. It sits somewhere around 2.5 times the mass of the Sun, perhaps a little less, perhaps a little more. And if the collapsing core is heavier than that, nothing we know of can stop it. No force, nothing. The collapse just keeps going down and down until the matter is crushed, past the point where any of our ordinary words even apply anymore. That a star's death must end this way under the right conditions. The black holes aren't some rare accident, but an inevitable outcome written into Einstein's equations that was proven by a physicist named Roger Penrose in 1965. His work showed that this collapse to a single point isn't a quirk of imagining a perfectly round, perfectly symmetrical star. It happens for real, messy, lopsided stars too. It is, in a sense, unavoidable. And for that work, more than half a century later, in 2020, Roger Penrose was given the Nobel Prize in Physics. So now we have our black hole, and we have around it that quiet edge, the event horizon. Let's finally look closely at it, the way I promised we would. The size of that edge has a name too. We call it the Schwarzschild radius, after the soldier from the trenches. And here's the lovely, simple thing about it. The more massive the black hole, the bigger that edge. It scales in the gentlest, most straightforward way. Double the mass, and you double the size of the horizon. Let me make that real for you in a way you can hold while you're drifting off. Take our own Sun. If you could somehow crush the entire Sun down small enough to become a black hole, its event horizon would be just about 3 kilometers across. The whole Sun, the thing that lights our days and warms our world, squeezed into a dark sphere, you could drive across in a couple of minutes.
And the Earth? If you wanted to turn our whole planet into a black hole, every ocean, every mountain, every city, you'd have to crush all of it down to a sphere about 9 millimeters wide. 9 millimeters, the size of a small marble. You could hold the entire Earth in the palm of your hand if it became a black hole. Imagine that for a moment, there in the dark.
Everything you've ever known, every place you've ever been, every person you've ever loved, all of it folded into a little marble resting in your hand. That's what the event horizon really is. Not a wall, not a surface, just a line drawn in space at exactly that distance, marking where the pull becomes so steep that even light, the fastest runner in all the universe, can no longer make it back out. And here is the quietly astonishing thing. Walk up to that line, that Schwarzschild radius, that invisible edge drawn in space, and nothing about it looks like anything at all. There is no wall there. There is no surface you could put your hand against. There is no glowing boundary, no rushing sound, no sign saying you have arrived at the point of no return. The event horizon is not a place in space the way a wall is a place. It is a relationship, a condition, a one-way agreement that space-time has made with itself. This is the first great reframe, and it is worth sitting with for a moment, especially if you're the kind of person who grew up picturing a black hole as a kind of hole, a dark tunnel in space, an opening to somewhere else, a drain in the fabric of the universe with something terrifying on the other side. That image is everywhere. It's in movies, in textbooks, in the way the very name pulls at the imagination. But it isn't quite right. There is nothing to fall through. A black hole is not a hole. There is no gap, no tunnel, no other side. There is simply a region of space-time where gravity has become so steep, so overwhelmingly strong, that the mathematics of escape no longer work in your favor. Think of it this way. Wherever you are right now, there is a speed at which a rocket would have to travel to escape the Earth's gravity entirely. We call it escape velocity. For the surface of the Earth, it's about 11 kilometers per second. Fast, but manageable for a spacecraft. Now, as you compress a mass down smaller and smaller, as you squeeze it tighter, concentrating its gravity into a smaller space, that escape velocity climbs. It climbs and climbs. At some critical radius, it reaches the speed of light, and since nothing can travel faster than light, nothing can escape from within that radius. That's all the event horizon is. It's the surface where escape velocity equals the speed of light. It is a threshold defined by physics, invisible to the eye, real as anything in the universe. And if you crossed it, if you were somehow able to drift across that line, you would not feel it happen. This is the part that takes a moment to absorb, the part that physicists call the equivalence principle, and it is one of the deepest and strangest gifts that general relativity gives us. If the black hole were large enough, the crossing would be genuinely unremarkable in the local sense. No shudder, no alarm, no sudden change in the air. The laws of physics in your immediate vicinity would look perfectly normal. You could be floating there, relaxed, and the horizon would pass through you like a ghost, and you would not know from moment to moment that anything had changed. You would simply be inside in a place from which there is no return, and the universe outside would go on, indifferent, as if nothing had happened. The reason for this comes down to tidal forces, which we'll get back to in a little while. But the short version is this: the event horizon of a sufficiently large black hole is a region where the difference in gravitational pull across your body, the stretch between your head and your feet, is still gentle. You feel nothing unusual. The danger comes later, deeper in. The horizon itself is simply the boundary where your future has been quietly decided for you. Not with a bang, just with a line. Now here is where time does something remarkable, something that makes this all feel a little more like a dream. the good kind, the kind that bends gently without breaking anything. Imagine you have a friend, a very trusting, very scientifically adventurous friend, and they agree to fall toward a black hole while you watch from a safe distance, floating in your spacecraft a comfortable way back. You watch through a very good telescope, and here is what you see. As your friend falls toward the event horizon, they slow down. Not because they're decelerating. In fact, from their own experience, they're falling faster and faster, pulled by gravity. But from your view, something extraordinary is happening to the light they're sending back to you. Gravity is so strong near the horizon that it bends and stretches the light itself. The waves of light take longer and longer to climb back out to you. The frequency of the light drops. Your friend's image shifts slowly from normal light toward red, toward deep red, toward infrared, toward wavelengths you can no longer see. And their motion, it appears to slow, to approach the horizon in the way that a hand approaches a wall in a dream, always getting closer, never quite arriving. You would watch your friend fall for what would appear, from your vantage point, to be an eternity. Their light redshifted to nothing, their motion frozen at the very edge of the horizon, their last moment stretched across time like a photograph left too long in the sun. You would never see them cross, not because they don't cross, but because the light that would carry that moment to you can never quite make it back. And your friend? From their perspective, they cross the horizon in a perfectly finite time. No drama, no freeze frame. They move through the boundary and keep going, and the universe outside doesn't pause or falter. They are simply inside now. Two experiences, two timelines, two descriptions of the same event. And both are correct. This is not a contradiction. It is not an error in the theory. It is the nature of space and time in the presence of extreme gravity. Time flows differently depending on where you are in a gravitational field. Deep in a well of gravity, time moves more slowly relative to somewhere high above it. And near a black hole, this effect becomes so extreme that the outside universe and the inside of the event horizon no longer agree on anything as basic as whether a moment has happened yet. It is genuinely one of the most disorienting things you can sit with. The idea that when did this occur does not have a single answer that everyone agrees on. That simultaneous is not a fixed thing. That the universe does not come with a universal clock ticking the same tick for everyone everywhere. Einstein showed us this more than 100 years ago, and the black hole is where it becomes not just theoretically true, but vivid and strange and almost visceral if you let yourself really lean into it. So your friend is inside. The horizon has passed. And there is at this point one very pressing question. What survives? What does the black hole actually remember about whatever has fallen in? The answer, it turns out, is almost nothing. There is a theorem in physics, elegant, a little eerie, and carrying the name the no-hair theorem, which is one of the more memorable names in all of science. The idea behind it is this: no matter what you throw into a black hole, no matter how complex or colorful or historically interesting the object was, the black hole will settle down into a state described by only three numbers. 3. Just 3. The first is mass, the total mass of the black hole, including everything that has ever fallen in. The second is electric charge. Most astrophysical black holes are expected to be nearly neutral. Opposite charges fall in together and cancel. But in principle, charge is one of the measurable quantities. And the third is angular momentum, or spin. How fast is the black hole rotating, and in which direction? Mass, charge, spin. That's it. 3 numbers. Those are the only properties a black hole is allowed to have. Everything else, the temperature of the star that collapsed to form it, the chemical composition of gas that spiraled in over billions of years, the memories and the history of whatever fell through the horizon. All of it is, from the outside, gone. Inaccessible. The black hole doesn't carry a record of what made it. It doesn't know its own history. It has no hair, as the physicists say, no identifying features beyond those three cold numbers. Werner Israel laid some of the mathematical groundwork for this in the 1960s, and Brandon Carter and Stephen Hawking helped prove it in progressively more general cases, until the theorem stood as a foundational result. What the no-hair theorem is really saying is something profound and a little unsettling. It's saying that black holes are, in a deep sense, the most featureless objects the universe allows. You could pour in a library of books, a civilization's worth of art, all the biological diversity of an entire planet, and the whole would process all of it and emerge indistinguishable from one that had swallowed nothing but hydrogen. The information, in some fundamental sense, disappears behind the horizon. We'll come back to what that really means, because it turns out the universe may not be as forgetful as it first appears, and some very serious physics has been built trying to understand whether anything is truly lost. But for now, settle with that image. Three numbers: mass, charge, spin. The rest is silence. And now let us talk about what happens to you, not your friend this time. You, if you were actually falling toward a black hole, not watching from a spacecraft, but genuinely, freely falling, pulled inward by gravity, what would you feel and when would you feel it? The answer depends entirely on the size of the black hole. And this is where the story of black holes does something that very few topics in science manage to do. It completely inverts your common sense. It takes your intuition and turns it gently upside down, the way gravity itself might, if gravity were feeling playful. Here is the principle, and then we'll let it sink in. Tidal forces, indeed the difference in gravitational pull between one side of your body and the other, scale in a very specific way with the mass of the black hole. As the black hole gets bigger and more massive, the tidal forces at its event horizon actually get weaker, not stronger, weaker. This sounds wrong. Surely a more massive black hole is more dangerous? And in a general sense, yes, more mass, more gravity. But the event horizon of a more massive black hole is also much, much farther out. The Schwarzschild radius grows with mass. And because the tidal force you feel depends on how much the gravity changes across the length of your body, and because that rate of change is gentler when the horizon is large and far from the singularity, it means the danger zone is effectively pushed farther inward. The place where tidal forces become lethal moves to deeper interior regions well inside the horizon. The result? A small black hole, a stellar mass black hole of say 10 or 20 solar masses, has a tiny event horizon just a handful of kilometers across. The tidal forces at that horizon are enormous, so enormous that if you were falling toward it, you would be pulled apart, stretched vertically like taffy, squeezed in from the sides, reduced to a thin strand of atoms and subatomic particles. Long before you ever reached the event horizon, you would be spaghettified, to use Stephen Hawking's actual, recognized, accepted scientific term, which somehow manages to be both precise and delightful, outside the black hole entirely. But a supermassive black hole, the kind that sits at the center of a galaxy, millions or billions of times the mass of our Sun, has an event horizon so large that the tidal forces there are almost gentle. Gentle enough that a person, or what remains of a person, could cross the horizon intact. Still alive, still aware, if we want to be generous with our imagination, still capable of marveling for whatever brief time remains at the fact that they have crossed the most famous boundary in physics and are still breathing. So the counterintuitive truth, the bigger the black hole, the safer the crossing. Small ones kill you on the way in. The giants let you through, at least at the gate. There is a word for this process of being stretched and squeezed into a thin strand: spaghettification. It is, as I said, the actual scientific term. Hawking used it in A Brief History of Time, and it stuck in the way that the best scientific nicknames always do. And what it describes is the action of tidal forces on an extended body, the fact that the side of you closer to the black hole is being pulled harder than the side of you farther away, and that this difference in force grows as you fall deeper. Your body, or any extended object, is simultaneously stretched in the direction of the gravitational pull and compressed in the directions perpendicular to it. The mathematics that describes it involves the mass of the black hole divided by the cube of your distance from the singularity. As that distance decreases, the tidal force grows fast, very fast. The cube in the denominator means the force does not just get larger, it becomes ferocious. And it is not only theoretical. In 2020, astronomers using the Very Large Telescope at the European Southern Observatory directly observed this happening. A star drifting too close to a supermassive black hole 215 million light-years away was pulled apart. The event was catalogued as AT2019-Keys. It was the closest tidal disruption event ever recorded at the time. Astronomers watched the stellar material stretch, wrap, and spiral, radiating brilliantly as the star's substance was consumed, a star becoming a strand, an entire sun reduced to a ribbon of light and gas curling toward a dark center. It was, in its terrible way, beautiful. And it was the most direct observation anyone had ever made of spaghettification at work. Now, let's say you managed to cross the event horizon of a very large black hole. You cross intact, alive, the tidal forces still gentle, the physics locally unremarkable. What is waiting deeper inside? Here, the honest and careful answer requires a moment of intellectual courage, because what the mathematics says is waiting inside at the very center of a black hole is a singularity, a point, or in the case of a rotating black hole, a ring, where the density becomes infinite, where the curvature of space-time becomes infinite, where the known equations of physics break down completely and return answers that have no physical meaning. Infinity showing up in the math of physics is almost always a sign that the theory you're using has reached its edge, has stepped off the map. The singularity is not a place where matter is literally infinitely dense. The singularity is a place where our current best theory, general relativity, can no longer describe what is happening. Roger Penrose proved in 1965 that singularities are not a quirk of perfect symmetry, not an artifact of assuming the collapsing star was exactly spherical. They form inevitably, robustly, under very general conditions of gravitational collapse. This was a deep result and a somewhat uncomfortable one. It meant that general relativity, as a theory, predicts its own incompleteness. It predicts the existence of regions where it cannot tell you what happens. For this insight, among others related to black holes, Penrose was awarded the Nobel Prize in Physics in 2020, a prize more than half a century after the theorem itself. Physics sometimes takes a long time to fully absorb its own discoveries. What we need, and do not yet have, is a complete theory of quantum gravity, a framework that marries the quantum mechanics of the very small to the curved space-time of general relativity. In such a theory, the singularity would likely be replaced with something finite, something strange perhaps, something we cannot yet imagine clearly, but something that doesn't require the universe to become infinitely dense in a finite region of space. The singularity is the place where the map runs out. It is not a claim that infinity is real. It is an honest marking of the boundary of what we currently understand. And so, somewhere inside a black hole, the laws as we know them end. Not with a bang, not with a wall, but with the gentle failure of the equations, a blank page where the next chapter of physics has not yet been written. Let's rest with that for a moment. You don't have to carry all of it at once. No rush. There is a darkness at the center of a black hole where our understanding stops, and there is perhaps something almost peaceful about that. An acknowledgement that the universe is larger and stranger than any single theory, and that the story is still unfinished, still being written somewhere in laboratories and chalkboards and late nights of quiet calculation. The universe has held on to this secret for now, held it behind an event horizon, behind the equation's edge. Wherever you are tonight, that mystery is still out there. Every black hole we have found in every galaxy we have mapped holds a version of that same blank space at its center. We have found dozens. We have found thousands. And each one holds the same question, sealed inside. But the blank at the center is not the end of what we know, not even close. Because as strange as the inside of a black hole is, as much as it defeats our current mathematics, what happens on the outside, and especially what happens at the boundary, the event horizon itself, turns out to be full of astonishing physics that we can actually say something about. Real, measured, verified, and in some cases directly observed physics.
And one of those things, the thing that will slowly pull us toward the end of this story, toward the end of time itself, is something that comes from asking a very simple question. Do black holes last forever?
You might reasonably assume they do. They are, after all, the objects from which nothing escapes. They seem to accumulate mass, not lose it. They pull everything toward them. They sit immovable at the hearts of galaxies, while stars are born and die, and the universe rearranges itself around them. If anything is permanent, surely it is a black hole. And yet, we are not quite ready to go there yet. The answer requires a little more groundwork, or a more complete picture of what black holes look like to the rest of the universe, not just to things falling toward them. Because before we can talk about how black holes end, we need to understand how brilliantly they shine. And that, as it turns out, requires us to revisit the second great reframe. The name black hole carries a very specific visual implication. It implies darkness. It implies absence. A region of space that is simply black. But the full truth is so much stranger, and so much brighter. Not every black hole is actively feeding. A black hole that is sitting quietly, not pulling in significant amounts of matter, does indeed appear dark against the sky. Its gravity curves light around it, casting a shadow, but it does not generate light of its own. If you could somehow see one against a bright background, you'd see the shadow, the dark center, the light bending around the edges. A black dot in the night. And for most of the supermassive black holes in the universe right now, including the one sitting at the center of our own Milky Way, this is roughly the state of affairs. Quiet, watchful, patient. But when a black hole is actively feeding, when material is falling toward it in significant quantities, everything changes. Everything becomes, in a sense, the opposite of dark. What happens is this. As gas, dust, and matter spiral toward the event horizon, they don't fall straight in. They carry angular momentum. They're moving sideways as well as inward. And so they spiral. They form a disk. A vast, flat, glowing ring of infalling material, circling the black hole like water approaching a drain, except incomparably hotter, incomparably more energetic. We call it an accretion disk. And the accretion disk is where extraordinary things begin to happen, simply through the violence of compression and collision. The material in the disk is not falling in gently, it is being compressed. Particles are crashing into each other. there is friction, an enormous, furious, constant friction, and friction generates heat. The inner regions of an accretion disk, the parts closest to the event horizon, can reach temperatures of millions of degrees. The surface of the Sun is about 5,500 degrees Celsius. The inner edge of an accretion disk around an actively feeding supermassive black hole can be hundreds of times hotter than that. At those temperatures, the disk doesn't just glow red or orange the way a warm coal does in a fireplace. It radiates across the entire electromagnetic spectrum. It blazes in visible light, in ultraviolet, in X-rays. The theoretical framework describing how this disk radiates, how the energy flows, how the luminosity is distributed, was worked out by Nikolai Shakura and Rashid Sunyaev in the 1970s, and the Shakura-Sunyaev model remains a foundational piece of accretion disk physics to this day. And so here is the extraordinary thing. The black hole itself, the event horizon, the region of no return, emits nothing. But the accretion disk just outside it, the last gasps of infalling matter, radiates more brilliantly than almost anything else in existence. Take a black hole of the right mass, with material falling in at the right rate, and what you get is a quasar. The word quasar is a contraction of quasi-stellar radio source, a name from the early days of their discovery, when these objects looked like bright points of light, like stars in the sky, but weren't stars at all. They're far too distant to resolve into anything with an extended shape in most early observations. They just look like very bright dots. And then astronomers began to measure their distances and found they were unimaginably far away, billions of light years across the universe. And something very far away that still appears this bright must be producing an almost incomprehensible amount of energy. What they are, we now understand, is this: a supermassive black hole that is actively accreting, actively feeding on an enormous amount of material. The accretion disk around it is so hot, so vast, so furiously energetic that it outshines everything else nearby. A single quasar can outshine its entire host galaxy. Not by a little, not by a factor of 2 or 10. A single quasar can emit more light than 100 or 1,000 or even 100 billion other stars, the entire stellar population of a galaxy combined, from a region smaller than our solar system. Our solar system stretches roughly a few light hours across, maybe a light day or two if you include the very outer reaches. And from a volume no larger than that, a quasar can pour out energy equivalent to the light of hundreds of billions of stars. This is the darkest object in the universe, producing the brightest sustained light the universe has ever made. The most luminous quasar ever discovered as of 2024 is catalogued as J0529-4351. This is the object announced by a team led by Christian Wolff and colleagues at the European Southern Observatory in 2024, and the numbers attached to it are simply staggering. J0529-4351 shines with a luminosity roughly 500 trillion times that of our Sun, 500 trillion. If you placed our Sun in one pan of a scale and tried to balance it with J0529-4351 in the other, you would need 500 trillion suns. This single object, this single feeding black hole, is the most luminous sustained source of energy ever observed in the known universe, and it achieves this by consuming matter at an extraordinary rate. The black hole at the heart of J0529-4351 is estimated to be consuming mass at roughly the equivalent of one entire solar mass per day. One sun every day falling in and being converted to energy. The accretion disk around it, the glowing ring of infalling matter, is estimated to span roughly 7 light years across. Light, the fastest thing in the universe, would take 7 years to cross from one side of this disk to the other. It is an object of almost meditative impossibility, and it is powered by darkness. The quasar light that reaches us from across the universe carries another layer of wonder too. The most distant quasars, the ones found at the highest redshifts, are so far away that the light reaching us now left them more than 13 billion years ago. We see them not as they are today, but as they were when the universe was less than 1 billion years old. When the cosmos was young and dense and wild, black holes were already enormous and already feeding voraciously, already pouring out light that would travel for more than 13 billion years just to reach our instruments. They are lighthouses from the universe's infancy, signals from a time before our own star existed, before our planet, before any of the history that led to this moment. We look back at them and we see the ancient universe lit by its darkest engines. And around some of these feeding black holes, there is something else entirely. Not just the disk below glowing and spreading outward in a flat plane, but something perpendicular to it, something vertical, something that reaches out into space for extraordinary distances, relativistic jets. Some actively feeding black holes, the precise mechanism is still not fully understood, channel a fraction of the accreting material into extraordinarily focused beams of plasma that are launched from the poles of the system perpendicular to the accretion disk at speeds exceeding 99% of the speed of light. These jets can extend for thousands or even millions of light years, far beyond the galaxy that hosts the black hole, into the vast intergalactic space beyond. Think about the scale of that. The black hole itself might have an event horizon spanning a few light hours to a few light days. The host galaxy might be 100,000 light years across, and the jet extends for millions of light years beyond even that. The black hole is generating a structure thousands of times larger than the galaxy it lives in, launched at nearly the speed of light, reaching out into the void between galaxies. The galaxy known as M87, a massive elliptical galaxy some 55 million light-years away in the Virgo cluster, has one of the most studied jets in the sky. The M87 jet was observed and photographed and analyzed for decades. Astronomers measured its apparent motion across the sky and found it appeared to be moving faster than the speed of light, which seems impossible, and is. But the effect is a geometric illusion, a consequence of the jet pointing almost directly toward us as it races outward. The jet from M87 was already a well-known object, already mapped and studied in detail, long before anyone had directly imaged the black hole at its core. That imaging came later, and it became one of the great moments of 21st century science. The black hole at the center of M87, designated M87 star or M87 takes, contains roughly 6.5 billion times the mass of our Sun. It sits 55 million light-years away. 55 million light-years. Light that left M87 before the first multicellular life appeared on Earth is only just arriving here now. And yet, from that unimaginable distance, a team of more than 200 scientists and engineers managed to produce an image of its shadow. The instrument they used was not a single telescope. No telescope on Earth could be built large enough to resolve something so far away. Instead, the Event Horizon Telescope collaboration linked radio observatories across the planet. In Hawaii, in Chile, in Spain, in Greenland, at the South Pole in Antarctica, and elsewhere, synchronizing them using atomic clocks, coordinating observations across the entire globe, and combining the data afterward using a technique called very long baseline interferometry. The effective diameter of this virtual telescope was the diameter of Earth itself. Not a telescope the size of a building or a mountain, but a telescope the size of a planet. The data produced by these observatories during the coordinated observation runs was enormous, far too large to send across the internet. The hard drives had to be flown physically on airplanes from Antarctica and from the various observatories to central data processing facilities in Massachusetts and Germany. 1/2 ton of hard drives, more than 1,000 pounds of storage media carried across oceans on commercial flights before the data could even begin to be assembled. And then the imaging. The image could not be produced in the usual way because the raw data doesn't look like a photograph. It has to be reconstructed using algorithms and mathematical techniques from the pattern of radio signals recorded across all those different locations. One of the key imaging algorithms was developed by Katie Booman, then a graduate student, who later became one of the public faces of the effort. The team used multiple independent methods, multiple algorithms, cross-checking each result against the others to ensure that what they were seeing was real, that the bright ring and the dark shadow at the center were genuine features of the object and not artifacts of the processing. On April 10, 2019, they released the image to the world, a bright, blurry ring of orange and gold glowing asymmetrically with a dark center. The shadow of the black hole, the region where light falling in is captured and never returned. Not the black hole itself exactly. There is no surface to photograph. But the shadow it casts on the glowing ring of light bent around it by gravity. The first direct visual evidence of a black hole. The first time human beings had ever seen something like this. And then, in 2022, the Event Horizon Telescope collaboration released a second image, this time of the black hole at the center of our own galaxy. Sagittarius A star, SGRA, the supermassive black hole at the heart of the Milky Way, roughly 4.3 million times the mass of our Sun, sitting about 27,000 light-years away from us, much closer than M87 cosmically speaking, though the intervening space is full of gas and dust that makes it harder to observe. It is, as black holes go, remarkably calm, sedate even. The material in its immediate environment is sparse. It doesn't have the roaring accretion disk that M87 occasionally shows. It is a very quiet eater. Someone once described Sagittarius A as eating so little, relative to its mass, that if it were a human being it would consume approximately 1 grain of rice every million years. Not every year, not every century, every million years. 1 grain of rice. The Milky Way's central black hole is, in the language of accretion, essentially fasting. But it is still there. 4.3 million solar masses, 27,000 light-years away, sitting at the center of the galaxy we live in. And now we have a picture of its shadow. A fuzzy golden ring, smaller and more turbulent-looking than M87's image, or data because SGRA is itself smaller, and because its turbulent inner environment changes faster, making it harder to image cleanly. But unmistakably, there, unmistakably real, our black hole. The one our Sun has been orbiting along with hundreds of billions of other stars for 5 billion years. And if we wanted to hear a black hole rather than see one, that too has been done. On September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected something that no instrument had ever detected before. A ripple in spacetime itself, a gravitational wave. Gravitational waves are distortions in the fabric of spacetime, compressions and stretches of the geometry of space that propagate outward from energetic events involving accelerating mass. They were predicted by Einstein in 1916 as a consequence of his general relativity. But for nearly a century, no one could detect them. They are extraordinarily weak by the time they reach us from any cosmic source. The instruments needed to detect them would have to be almost unimaginably sensitive. LIGO consists of 2 L-shaped detectors, one in Hanford, Washington, and one in Livingston, Louisiana, each with arms 4 kilometers long. A laser beam is split and sent down each arm, bouncing off mirrors at the far end and returning. If a gravitational wave passes through, it stretches space in one direction and compresses it in another. And this tiny difference in the length of the 2 arms is what the instrument measures. The stretching and squeezing that LIGO detected on September 14, 2015, from the event catalogued as GW0529-4351, was a change in the length of the 4-kilometer arms of about 0.004 of a femtometer. To give you a sense of scale, a proton, the particle at the heart of every atom, is about a femtometer across. LIGO detected a change in distance smaller than 1/10,000th the width of a single proton, in arms 4 kilometers long. This is one of the most precise measurements in all of human history. What caused it was two black holes, roughly 36 and 29 times the mass of our Sun, that had been orbiting each other for billions of years in a slowly decaying spiral, losing energy to gravitational waves, drawing closer and closer over cosmic timescales. And then, in a fraction of a second, they collided and merged. The event happened approximately 1.3 billion light-years away, and in that final fraction of a second, the merging black holes converted something like 3 solar masses, at the entire mass of 3 suns, into pure energy. Pure gravitational wave energy. Briefly, in that tiny sliver of time, the merger radiated more power than all the stars in the observable universe combined. Every star in every galaxy we've ever seen, all of them burning at once, and this single merger, for that fraction of a second, outshone all of them. What LIGO recorded was the sound of that. Not literally. Gravitational waves are not sound-waved, but the signal, when converted to an audio frequency, becomes a rising tone, a chirp. It starts low, rises in pitch and intensity over a fraction of a second, and then there's a brief ring down as the merged object settles. The chirp lasted about 0.2 of a second. 0.2 of a second, and it was the audio signature of two black holes, each roughly 30 times the mass of our Sun, merging and becoming one. When scientists played it the first time in the announcement in February 2016, the room laughed in astonished delight. That's the sound of it. That little blip, that rising chirp, is one of the most violent events in the observable universe, and you could play it on a speaker and your cat would probably ignore it entirely. The discovery won the 2017 Nobel Prize in Physics for Rainer Weiss, Barry Barish, and Kip Thorne. And it opened a new era of astronomy, the ability to listen to the universe, not just look at it. Since then, the LIGO, Virgo, and CAGRA collaborations, with the LVK collaboration, have detected dozens more gravitational wave events, including one, GW0529-4351, which produced a merged remnant of roughly 142 solar masses, a previously unexpected mass range that raised new questions about how such heavy black holes form. And so we have seen black holes in radio images, we have heard them in gravitational waves. We have watched one tear a star apart from 215 million light-years away. We have measured the spin of black holes like NGC 1365, whose central black hole spins at roughly 84% of the maximum physically allowed rate, with some measurements of other black holes approaching 99% of the speed of light at the event horizon. We have measured the glow of accretion disks. We have seen relativistic jets stretching millions of light-years. We have found the most luminous object in the universe and traced its light back more than 13 billion years. We have not visited one. We have not sent a probe through an event horizon, and we wouldn't get the data back if we tried. But we have come extraordinarily far, from a theorem solved in a trench in 1916 to a 500 trillion sun quasar announced in 2024. The universe has been willing gradually to give up some of what it knows. And now there is one question this whole journey has been building toward. The question the title of this night's quiet tour has been promising since the very beginning. Not just what a black hole is or how it looks or what it does to things that come too close, but whether black holes last forever, and if they don't, what comes after them? What comes at the very end? The answer, as with so many answers when it comes to black holes, starts with something that at first seems impossible. A realization that took even Stephen Hawking by surprise, that overturned what many physicists believed, and that eventually led him to one of the most famous theoretical results in the history of physics. The answer begins with a question about emptiness, because it turns out that empty space, truly empty space, the vacuum, the nothing between things, is not quite as empty as it appears. And what lives in that apparent nothing has everything to do with how a black hole ends. But that, as they say, is the next mystery waiting in the dark. And we'll walk into it slowly together in just a moment. So let us talk about light. Not the soft lamp still glowing in your room, not the faint blue of whatever screen you carried to bed tonight. The brightest light in the known universe. The kind of light that makes every star you have ever seen, every constellation, every planet and galaxy visible to the naked eye look like a candle held up against the sun at noon. That light comes from a black hole. And before we go any further into the darkness, into the evaporation and the end of time, before any of that, we need to sit with that for a moment, because it is genuinely one of the most counterintuitive facts in all of astrophysics, and it deserves to land properly. You spend the first part of any black hole story being told about something dark and silent and invisible, a region of space that captures everything and releases nothing, a place where even light vanishes. And then the universe turns around and tells you that the darkest objects it contains are also the source of the most extraordinary light it has ever produced. This is reframe number 2, and it is one of the most startling pivots in science. Here is what actually happens when a black hole feeds.
Matter does not simply fall in, it does not drop straight down into the event horizon the way a stone drops into a well. Matter that approaches a black hole from any angle carries momentum, carries rotation, carries a direction of travel. And so instead of plunging straight in, it spirals. It joins a flattened, rotating disk of gas and dust and torn stellar material that accumulates around the hole's equator. This is called an accretion disk.
And it is, in the truest sense of the word, a machine. As material in the disk spirals inward, the inner layers move faster than the outer layers. The gas closer to the hole is moving at a higher orbital velocity than the gas farther out, and so there is constant friction between them, constant shearing, constant collisions between particles moving at different speeds in different directions. That friction converts kinetic energy into heat, and when we say heat, we do not mean warmth. We mean temperatures of millions of degrees. The inner regions of an accretion disk around an actively feeding black hole reach temperatures comparable to the cores of stars, and sometimes far beyond. At those temperatures, matter doesn't just glow, it blazes across the entire electromagnetic spectrum. Visible light, ultraviolet radiation, X-rays, pouring energy outward in all directions. The accretion disk is not a new idea. The basic physics of how infalling gas releases energy was formalized in the 1970s by two Soviet physicists, Nikolai Shakura and Rashid Sunyaev, whose model of disk accretion became one of the foundational frameworks of modern astrophysics. The Shakura-Sunyaev model described how the structure of the disk, the temperature profile from outer to inner edge, the luminosity of the whole system, all follow from the physics of viscous rotating gas. It is not a speculation, it is a well-tested piece of machinery that underlies much of what we now know about feeding black holes. And when that machinery runs at full power in a sufficiently massive black hole with a sufficiently rich supply of gas, what you get is called a quasar. Quasar, the word comes from quasi-stellar radio source, a label that astronomers in the 1960s gave to objects that looked like stars in photographs but behaved nothing like stars in their spectra. The light coming off them was wrong for a star. And when the distances were worked out, when astronomers understood just how far away these things were, the energy implied by their brightness was staggering. You could not explain that luminosity with a star, or with a cluster of stars, or even with millions of stars. The only mechanism that could account for it was a supermassive black hole gorging itself on infalling matter, with the accretion disk radiating the released energy across the whole sky. A quasar is a feeding supermassive black hole. That is all it is. A black hole with enough material falling into it to power a disk of extraordinary luminosity. And the numbers? The numbers are difficult to hold in the mind all at once. A single quasar can outshine its entire host galaxy. Not match it, not rival it, outshine it. A single compact region, smaller than our solar system, pouring out more light than hundreds of billions of stars combined. Think about the Milky Way, somewhere between 100 billion and 400 billion stars, stretching 100,000 light-years across, every one of them fusing hydrogen into helium, pouring energy into the cosmos. And a quasar, from a region you could fit within the orbit of Neptune, outshines all of that. 100 galaxy worths of starlight, sometimes more, from a pinprick of space. The most luminous known quasar, J0529-4351, was announced in 2024 by astronomer Christian Wolf and his colleagues at the European Southern Observatory. It shines with roughly 500 trillion times the luminosity of the Sun, 500 trillion, and it sustains that luminosity by consuming approximately 1 solar mass of material every single day. Every day, a quantity of gas equivalent to the entire Sun falls into this object and is converted by the violent alchemy of the accretion disk into outgoing light and heat. The accretion disk surrounding J0529-4351 is approximately 7 light-years across, an enormous flattened ring of blazing matter wider than the distance from our Sun to its nearest stellar neighbor. It is, by measurement, the most luminous sustained object ever observed in the universe, and it is powered by the darkest thing in the universe. That tension, the darkness, feeding the brightness, the invisible engine behind the most visible light, is part of what makes black holes so philosophically disorienting. We named them for the dark. We think of them as objects of absence, silence, taking. And in a sense that is true, but the reality is that a black hole in the act of feeding is anything but quiet or dark. It is a cosmic lighthouse. It is, in the most literal measurable sense, the brightest kind of object there is. The most distant quasars we can observe are seen as they were more than 13 billion years ago, their light traveling to us across the better part of the observable universe's entire history. When we look at them, we are seeing the early universe at work, seeing supermassive black holes that somehow reached billions of solar masses within the first billion years of cosmic time. How they grew so large so quickly is still an active area of research. There are open questions, careful papers, ongoing debate. But there they are, those ancient blazing beacons, bright enough to be seen across time itself, powered by the most extreme gravitational machinery the universe has on offer. Quasars, then, are black holes caught in one particular moment of their lives. The feeding moment, the bright moment. Many galaxies, including our own Milky Way, contain a supermassive black hole at their center that is not actively feeding at this moment. Sagittarius A, the 4 million solar mass black hole sitting at the center of our galaxy, is quiet, practically dormant. But the galaxies hosting the most brilliant quasars have black holes at their cores, surrounded by an abundance of gas and dust and stellar material, and those holes are eating, actively, constantly, producing the kind of light that travels 13 billion years and still registers on our telescopes. The universe lit its candles with its darkest objects, That is what a quasar is. Now, while we are thinking about the accretion disk, while we have that spinning, heated, brilliantly radiating structure in mind, there is one more feature of feeding black holes that deserves its own moment, because the accretion disk is not the only thing these objects produce. Some of them produce something else entirely, something that reaches even farther than the light from the disk: relativistic jets. When a black hole is feeding and spinning, most black holes spin, as we said earlier, the combination of its rotation and the magnetic field generated in the surrounding plasma can, under the right conditions, extract energy from the spin itself and funnel it into two narrow beams of material launched from the poles of the system. These jets are composed of plasma, of electrons and ions, accelerated to extraordinary speeds. The speeds we are talking about are over 99% of the speed of light. Material moving at over 99% of light speed, collimated into a beam, extended outward from the black hole's poles into surrounding space. And when we say extended outward, we mean extended far. These jets can stretch for thousands of light years, tens of thousands of light years, sometimes millions of light years. Structures larger than entire galaxies launched by the rotational energy of a black hole. The most famous example is the jet from the galaxy M87. The galaxy M87 sits about 55 million light-years away in the Virgo galaxy cluster, and at its center is the supermassive black hole we now call M87, which we will return to very shortly. The jet from M87 was known to astronomers long before anyone had ever imaged the black hole itself. It is visible in optical telescopes, in radio observations, in X-ray astronomy. A stream of plasma and energy launched from the galactic nucleus and extending outward, visible from 55 million light-years away. We photographed the jet of M87 before we ever photographed the hole that produced it. The jet had been studied, measured, observed for decades. The hole itself remained unseen, a presence inferred from the jet, from the motion of stars near the galactic center, from the sheer scale of what it was clearly producing. And then, in 2019, we finally saw it. But before that photograph, let's linger for just a moment on the spin itself, because the spin of a black hole is not a minor detail. It is one of the only three things a black hole possesses: mass, electric charge, and spin, the three properties of the no-hair theorem. And spin turns out to matter enormously for how the hole interacts with its surroundings. Black holes in nature spin fast, remarkably fast. When we say they spin, we mean the space-time around them rotates. The hole drags the fabric of space itself around with it, a phenomenon called frame dragging, a prediction of Einstein's general relativity that has been experimentally confirmed in weaker forms around the Earth. Around a spinning black hole, space itself swirls. An object near a spinning black hole is pulled not just inward, but also rotationally, dragged along in the direction of the hole's rotation, even if it has no velocity of its own. The theoretical maximum rate of spin for a black hole is tied to its mass. There is a limit, beyond which the geometry of space-time no longer permits a horizon to form. Real black holes are measured as a fraction of that maximum rate. In 2013, a team led by Guido Risoliti used observations from two space telescopes, NASA's NuSTAR and the European Space Agency's XMM Newton, to measure the spin of the supermassive black hole at the center of galaxy NGC 1365, about 60 million light-years away. The measurement published in Nature found that this black hole is spinning at roughly 84% of the theoretical maximum. And that figure, high as it is not close to the record. Some black holes have been inferred to spin at over 99% of the speed of light at their event horizons. The horizon of a maximally spinning black hole is moving at nearly the speed of light, and space-time around it is correspondingly twisted into extraordinary shapes. It is inside that spinning, feeding, blazing context, a supermassive black hole with an accretion disk and relativistic jets and a space-time geometry tortured by rotation, that the question finally became, can we actually see one? The answer arrived on the morning of April 10, 2019. The image was released simultaneously at press conferences on several continents. It showed a bright ring of light, slightly asymmetric, glowing orange and gold against the black of space, with a darker central region, the shadow of the black hole, the zone where light could not escape. It was not sharp the way a photograph of a planet is sharp. It was the size of an orange on the moon seen from Earth. But it was real. It was a direct image of a black hole's shadow, and nothing remotely like it had ever been published before. The object was M87 Loud, 6.5 billion solar masses. A black hole more than 1,000 times more massive than Sagittarius AB, sitting at the center of the giant elliptical galaxy M87 55 million light-years away. To image something that small and that distant required a telescope with extraordinary resolving power, and no single telescope on Earth, not the largest radio dish, not the best optical instrument, could achieve it. So the Event Horizon Telescope did something remarkable. It built a telescope the size of the entire planet. The Event Horizon Telescope is not one instrument. It is a network of radio observatories spread across the globe, linked together in a technique called very long baseline interferometry. By precisely synchronizing observations at radio dishes in Hawaii, in Chile, in Spain, in Mexico, in the American Southwest, and at the South Pole in Antarctica, the team created a virtual telescope whose effective diameter was the diameter of the Earth itself. An Earth-sized radio telescope, sharp enough, the collaborators like to say, to read a newspaper in New York from a cafe table in Paris. The observations were carried out over several nights in April 2017. The collected data was enormous. The hard drives filled up at the observing sites faster than they could be transmitted over the internet. The bandwidth required to send the raw data was simply not available, so the hard drives were packed up and shipped physically, flown on airplanes across the world, collected at data centers where teams of scientists began the long, painstaking work of combining the signals from all those separate dishes into something coherent. The total data filled approximately 1/2 ton of hard drives, and the analysis that followed was not a matter of pressing a button and seeing an image emerge. It was a careful, deliberate, cross-checking process. The team produced the image using multiple independent algorithms, multiple independent teams of researchers working without knowledge of each other's results, so that when the images were compared and found to agree, when the same glowing ring appeared no matter which method was used, they could be confident it was real and not an artifact of any single technique. One of the key figures in developing those imaging algorithms was a graduate student named Katie Booman, then at the Massachusetts Institute of Technology. She had been working on the computational problem of turning sparse, noisy radio data from across the planet into an image of something no one had ever seen. The algorithm she helped develop was one of several independently run on the data, and when all the methods converged on the same glowing ring, it was, in her words, like finding a butterfly hidden in the data. The collaboration as a whole involved more than 200 scientists from around the world, each contributing a piece of the extraordinary technical challenge. The image was a collective achievement of the kind that science occasionally produces, a result that required not just talent or funding, but a peculiar combination of ambition, patience, and planetary coordination. The bright ring in the image is not the accretion disk itself, though the disk's emission contributes to the light. What the bright ring represents is the photon sphere, a region just outside the event horizon where light, bent by the extreme curvature of spacetime, can travel in unstable circular orbits. Some of that light escapes toward us, brightened and redirected by the gravitational lensing of the hole's immense mass. The dark central region, the shadow, is the area from which no light reaches us, bounded by the photon sphere. It is not a photograph of the event horizon itself. It is a photograph of its shadow cast against the glowing background of light orbiting and escaping near the horizon. But it is functionally the first time we had ever seen the shape of a black hole's gravitational influence on spacetime directly imprinted on an image. M87 is an extraordinary object, even by the standards of supermassive black holes, 6.5 billion solar masses, an event horizon so large that our entire solar system, all 8 planets, and the Sun would fit inside it with room left over, and it is the source of that visible jet of plasma we mentioned earlier, the relativistic jet extending outward from the galactic nucleus, a direct consequence of its spin and the magnetic fields threading the accretion disk. The image of M87 did not resolve what is inside. It did not answer the singularity question. It did not show us what happens to matter beyond the horizon, but it confirmed visually and directly that the object at the center of M87 has the shape and shadow predicted by general relativity for a black hole of its mass. Every feature of the image, the ring's brightness asymmetry, the size of the shadow, the geometry of the light, matched the predictions of the theory to within observational uncertainties. General relativity, tested in the most extreme environment we can observe, passed. 3 years later, in 2022, the Event Horizon Telescope published a second image, this time of the black hole at the center of our own galaxy, Sagittarius AI, 4.3 million solar masses. Located approximately 27,000 light-years from Earth, deep inside the dense central region of the Milky Way. Closer to us than M87 by a factor of 2,000, but far smaller and far less massive. Imaging Sagittarius A was in some ways harder than imaging M87L, despite its comparative proximity. The challenge is that M87L is massive and slow-varying. Light takes days to orbit its horizon, and over the course of an observing session, the structure of the accretion flow changes relatively slowly. Sagittarius A is much smaller. Light takes only about 4 to 5 minutes to orbit its horizon. During the hours of observation required to combine data from around the world, the appearance of Sagittarius A changes, scintillates, flickers, like trying to photograph a rapidly moving subject with a very long exposure. The team had to develop additional techniques to account for this variability, averaging across many snapshots of a structure that would not sit still. And yet the image, when released, showed the same essential structure as M87-, a bright ring of light surrounding a central dark shadow, a different black hole, a different size, a different mass, a different galaxy, but the same physics, the same geometry, the same signature of general relativity at work. Sagittarius A is, by any measure, a quiet black hole. The supermassive black hole sitting at the center of our own galaxy, 27,000 light-years away, is not currently feeding in any significant way. It flickers occasionally, a small burst of X-rays here, a brief brightening there. But compared to a quasar, compared even to many of the other galactic center black holes in our cosmic neighborhood, it is essentially dormant. The collaborators of the Event Horizon Telescope, when they gave a sense of just how little material Sagittarius A consumes, put it this way. If you imagined a human of average appetite scaled down to the feeding rate of SQR A punct relative to its mass, that person would eat a single grain of rice approximately once every 1,000,000 years. 1 grain of rice, 1,000,000 years. It is not starving, it is simply at rest, as black holes in quiet galaxies sometimes are, the material around it not presently arranged in any way that funnels significant quantities inward. Our own cosmic center is calm, and that is, in a strange way, fortunate for us. A Milky Way with an actively feeding quasar at its heart would be a very different place. The image of Sagittarius A, released in 2022, was the second direct photograph ever taken of a black hole's shadow. The first was 3 years old, and in those 3 years the field had not paused, had not rested on the achievement, but had been working steadily toward more. The Event Horizon Telescope has ongoing plans to add more dishes, to observe at higher frequencies, to eventually produce not just images but movies of the region around a black hole's shadow, watching material orbit and flicker and fall. We are, by astronomical standards, very new at this. We have 2 photographs of black hole shadows, 2. And we are treating them as the beginning of an observational tradition, not its pinnacle. But the year 2015 had already given us something different, something that did not produce an image at all, something that produced a sound, not a sound you could hear with your ear in the ordinary sense, a sound that was translated, shifted in frequency, rendered into something audible after the fact from a signal that had arrived as a tiny, precise oscillation in spacetime itself on September 14, 2015 at 5:51 in the morning, Eastern Time in the United States. 2 detectors belonging to the Laser Interferometer Gravitational Wave Observatory, LIGO, registered a signal that would, over the following months, be confirmed as the first direct detection of gravitational waves. Gravitational waves are ripples in the fabric of space-time itself, predicted by Einstein's general relativity, but not confirmed by direct detection for the better part of a century after he first described them. When massive objects accelerate, when they orbit one another or collide, they disturb space-time the way a moving object disturbs the surface of water, sending ripples outward at the speed of light. For the distortion to be measurable at the distances astronomers deal with, you need objects of extraordinary mass undergoing extraordinary acceleration. 2 black holes, spiraling together and merging, fit that description. The signal LIGO detected on September 14, 2015 was given the designation GW150914. It had been traveling for 1.3 billion years. It came from a pair of black holes, one with a mass of approximately 36 times the Sun, the other approximately 29 solar masses, that had been orbiting each other in a tightening spiral, losing energy to gravitational wave emission, drawing closer and closer until they finally merged into a single remnant black hole. The merger produced a remnant of approximately 62 solar masses, which means that roughly 3 solar masses, 3 times the mass of our Sun, were converted into pure energy in the form of gravitational waves in a fraction of a second. 3 solar masses of energy radiated in a burst lasting less than a second. For that brief moment, the power output of this merger exceeded the combined luminous power of every star in the observable universe, and the signal that arrived at LIGO after traveling 1.3 billion years through space, the entire whisper of that catastrophic event, moved the mirrors of LIGO's 4-kilometer detector arms by a distance smaller than 1/10,000th the diameter of a proton. Let that sit for a moment if you can. The detectors are 4 kilometers long, 4,000 meters, and the distortion in their length that encoded the collision of 2 black holes a billion years ago was smaller than a subatomic particle, smaller than 1/10,000th of a proton. The fact that we can measure anything that small is one of the genuine engineering miracles of modern science. LIGO did not happen quickly. It was the product of decades of development, refinement, testing, instruments that had to be isolated from every conceivable source of vibration, including the footsteps of people nearby, including ocean waves breaking on distant shores, including, at one point during commissioning, the distant rumble of a logging truck on a road miles away. When the signal was converted to sound, when the oscillation was translated into an audio frequency humans could hear, it made a brief rising tone, a chirp. It lasted approximately 0.2 seconds. And that rising tone, that brief ascending note, was the sound of two black holes finding each other after 1 billion years, speeding up, merging, and sending a shudder through the fabric of space itself that eventually rippled into our detectors on a September morning. The detection was announced in February 2016. It won the Nobel Prize in Physics in 2017. Since that first detection, the network of gravitational wave observatories, LIGO, joined by Virgo in Europe and KGRA in Japan, together forming the LVK collaboration, has catalogued dozens of events, merging black holes, merging neutron stars, mixed events where the nature of one of the objects is uncertain. The observations have revealed things that surprised astrophysicists. Among the surprises was an event called GW0990-521, detected in May 2019, which produced a remnant black hole with a mass of approximately 142 solar masses, placing it in what had previously been considered a problematic range. There are theoretical reasons to expect a gap in the mass distribution of black holes formed from stellar collapse, a region where the physics of stellar evolution should not easily produce black holes. GW090521 produced a remnant squarely in that gap. How it got there is still being worked out. Perhaps it formed from the merger of two smaller black holes in a dense stellar environment. Perhaps the stellar physics is more complex than the models assumed. The event did not resolve cleanly into any single existing explanation. That is often how it goes in gravitational wave astronomy. Each new observation brings not just confirmation but also new puzzles, a population of objects behaving in ways that were not fully anticipated, filling in a mass spectrum that turns out to be richer and stranger than the models predicted. We have, in a decade, gone from no direct detections of gravitational waves to a catalogue of dozens of events. We have heard black holes merging at distances of billions of light-years. We have measured the mass of remnants, the spins of the merging holes, the distances and directions, a new kind of astronomy done entirely in the language of space-time distortions rather than light. And what all of this, the accretion disk, the quasar luminosity, the relativistic jets, the EHT images, the LIGO chirp, what all of this amounts to is a picture of black holes as some of the most energetically significant objects in the universe. Not passive pits, not silent voids, active, spinning, radiating, merging, jet-launching engines that have shaped the galaxies around them and continue to shape the fabric of space-time itself. We have seen the brightest thing in the universe, and it is fed by a black hole. We have seen the shadow of a black hole imprinted in the warped light around it, in a photograph assembled from 1/2 ton of hard drives. We have heard two black holes collide in the vibrations of a detector arm moved by less than the width of a subatomic particle. All of that is part 3 of this story, and all of it is still the bright part, the feeding, the glowing, the merging. These are the events of the universe's middle history, when matter is abundant and black holes are actively engaged with the cosmos around them. But we began this tour with a promise. Not just what black holes are and how they shine. The title tonight named the other end of the scale, the smallest and the end of time. And to reach the end of time, we need to take one more step. A step that Stephen Hawking took in 1974 and that changed everything the physics community thought it knew about the permanence of these objects. Because there is a version of the black hole story in which they are forever, in which they outlast every star, every galaxy, every other structure in the universe, surviving through cosmological timescales that make the current age of the universe look like the blink of an eye, in which the last black hole is the last organized thing in existence, and its death is the last event that will ever happen. That version requires Hawking radiation. And Hawking radiation requires us to talk about the vacuum. here is the thing about empty space, or rather, here is the strange thing about empty space, the thing that quantum mechanics discovered, and that general relativity, in the hands of Stephen Hawking, turned into a statement about the fate of black holes. Truly, empty space, the vacuum, the nothing between things, is not actually empty. Quantum mechanics tells us that the vacuum is filled with fluctuating quantum fields, and that from those fluctuating fields, pairs of particles can momentarily appear and then annihilate each other, returning their borrowed energy to the vacuum. These are sometimes called virtual particles, though the name is slightly misleading. They are better thought of as fluctuations in the underlying quantum fields, brief disturbances that arise and resolve. In flat, ordinary space-time, these fluctuations cancel out. They appear and disappear without leaving any lasting trace. But near the event horizon of a black hole, the situation is different. The event horizon introduces an asymmetry. On one side of it, space is ordinary. On the other side, nothing can escape. And Hawking showed in a calculation published in Nature in 1974 that this asymmetry causes the vacuum fluctuations near the horizon to behave in a way that results in a real, outgoing thermal radiation, a faint glow of particles that carries energy away from the black hole. Not from inside the hole, nothing escapes from inside, but from the quantum vacuum in the curved space-time just outside the horizon. From outside, it looks exactly as if the black hole has a temperature and is radiating like a warm object. This is Hawking radiation. And its existence means that black holes have a temperature, lose energy, and, given enough time, evaporate. But how much time? Here is where the story becomes almost geological in its patience. The evaporation timescale for a black hole depends on its mass, and it scales with the cube of that mass. A more massive black hole evaporates far, far more slowly. And the Hawking temperature, the temperature at which the hole radiates, scales inversely with mass. Bigger holes are colder, much colder. A stellar mass black hole, say 10 times the mass of the Sun, has a Hawking temperature of about 100 billionth of a Kelvin. A supermassive black hole, like Sagittarius A cake, at 4.3 million solar masses, has a Hawking temperature of approximately 1.5 times 10 to the minus 14 Kelvin. For context, the coldest temperature ever achieved in a laboratory on Earth is a fraction of a billionth of a Kelvin above absolute zero. The cosmic microwave background, the afterglow of the Big Bang, the thermal bath of radiation that pervades all of space has a temperature of about 2.7 Kelvin. 2.7 Kelvin, which is cold, is still billions upon billions of times hotter than the Hawking temperature of Sagittarius A is. This means that right now, today, in the universe as it currently exists, Sagittarius A is not evaporating, it is doing the opposite. The black hole is absorbing energy from the cosmic microwave background, radiation flowing in from the universe around it, at a rate that far exceeds the faint trickle of Hawking radiation it emits. It is, in a sense, gaining weight from the ambient warmth of the cosmos. This will change. The universe is expanding, and as it expands, the cosmic microwave background cools. The temperature of that background radiation drops over cosmological time. Eventually, I am in the distant future, after timescales so vast they dwarf the current age of the universe, the background temperature will fall below the Hawking temperature of the black hole. Only then will the black hole begin to truly lose more energy than it gains. Only then will evaporation begin in earnest. And once it begins, it takes a very, very long time to finish. The evaporation timescale for a black hole, the mass of Sagittarius A, is on the order of 10 to the 87th to 10 to the 100th years. Written out, that is a 1, followed by somewhere between 87 and 100 zeros. The current age of the universe is approximately 14 billion years, 1.4 times 10 to the 10th. The evaporation time for our own galaxy's central black hole is longer than the current age of the universe by a factor of roughly 10 to the 77th. That is not a typo. That is not an approximation that rounds to something more manageable. It is genuinely, incomprehensibly longer. A stellar black hole, 10, 20 solar masses, evaporates faster because it is smaller and therefore hotter and therefore radiates more intensely. A stellar black hole's evaporation timescale is on the order of 10 to the 67th years, still a number that makes the age of the universe look like an infant's first breath. And the smallest black holes, the ones at the bottom of the mass scale, the primordial black holes hypothesized to have formed from density fluctuations in the first moments after the Big Bang, those evaporate fastest of all. A black hole with the mass of a large mountain, approximately 10 to the 11th kilograms, would have a Hawking temperature high enough that it would be radiating intensely right now and would finish evaporating today, or in the very recent cosmological past, ending in a final explosive burst of gamma rays. Searches for precisely such bursts have been conducted using instruments like the Fermi Gamma Ray Space Telescope. So far, no such signal has been convincingly detected, which places limits on how common primordial black holes of that mass can be. As a black hole evaporates and loses mass, its temperature rises, and as the temperature rises, it evaporates faster. The process accelerates. The final moments of a black hole's life, the last fractions of a gram of mass remaining, the last instants before the horizon shrinks to nothing, are not slow and gradual, but rapid and explosive. The final evaporation is a flash, a burst of high-energy radiation in the last tiny fraction of a second. Whatever the black hole once contained, whatever stars, planets, civilizations, history fell into it over its lifetime, that entire history exits at the end as a burst of thermal radiation and high-energy particles. Whether the information about what fell in is actually preserved in that final radiation, or whether it is genuinely lost, is the information paradox, and we will arrive there very soon. But first, just the shape of this inverted hierarchy deserves a moment of quiet attention. Bigger is colder, slower, more enduring, more patient. Smaller is hotter, faster, more explosive, more brief. The intuition you bring to this from everyday experience, that something big has more power, more force, more presence than something small, is exactly backwards when it comes to black holes and their relationship with temperature and time. The smallest black holes burn brightest and die soonest. The largest live longest in cold, faint, nearly imperceptible patience. And somewhere between the stellar mass holes that will outlast all the stars by 67 orders of magnitude and the supermassive monsters that will outlast even them by decades of additional zeros, lies the entire future history of the cosmos, which is where we are heading, just on the other side of one more rest stop. The information paradox, then the largest black holes, then the black hole era, then the last evaporation and the end of time. But those are waiting for the next passage of this quiet night. Settle in a little more if you're still comfortable. We'll get there slowly. So, the information paradox, let's rest here for a moment in this strange corner of physics before we move to the largest of all black holes and the final fate of everything. The paradox begins with a deceptively simple question. When something falls into a black hole, and the black hole eventually evaporates away through Hawking radiation, what happens to the information about what fell in? In physics, information doesn't quite mean what it means in ordinary speech. It doesn't mean knowledge exactly, or data in any digital sense. It means something deeper and stranger. It means the complete description of every particle, every quantum state, every property of everything that has ever existed. In the physics of the very small, in quantum mechanics, there is a rule, a foundational rule, that information is never truly destroyed. You can scramble it, compress it, hide it, transform it into something almost unrecognizable, but it is always, in principle, recoverable. The universe keeps its records. That is the rule, and black holes appear to break it. When matter falls into a black hole, it vanishes from the outside universe. That much is physically clear. The event horizon is a one-way gate, and then, when Hawking radiation eventually carries the black hole's mass away, that radiation is, according to Hawking's original calculation, purely thermal, random, like the glow of a warm object in a dark room. It carries no particular memory of what fell in. A book thrown into the fire, you might say. The fire is the same fire whether you burned a novel or a telephone directory. The ashes don't know the difference, and neither does the Hawking radiation. But quantum mechanics says that can't be right. The fire analogy actually breaks down even in ordinary physics. The smoke, the light, the heat. In principle, if you could measure every photon of the fire with perfect precision, the information from the book is still there, encoded in the correlations between the particles. Scrambled almost beyond any hope of recovery, yes, but not destroyed. Black holes appeared to be different. They appeared to actually destroy it, not scramble it, not encode it in some impenetrable form, just erase it. This is what Stephen Hawking argued in 1976, 2 years after his discovery of Hawking radiation, and it set off one of the deepest and most productive arguments in the history of theoretical physics, an argument that has not fully ended even now. In 2004, Hawking conceded a bet he had made with the physicist John Preskill on this very question. He said publicly that he had been wrong, that information is probably not destroyed, that it does escape somehow in the Hawking radiation, encoded in correlations too subtle for his original calculation to capture. He gave Preskill a baseball encyclopedia. "Information in this form," he reportedly said. Preskill joked he would have preferred it in digital form. But even conceding the bet, even agreeing that information probably escapes, the mechanism, how it escapes, what form it takes, how the random-looking thermal radiation can carry the complete history of everything that fell in, remained deeply mysterious. In the years since, physicists have made real progress on a related question. They've shown that if you track the quantum entanglement between the Hawking radiation emitted early in a black hole's life and the radiation emitted later, the information is not lost, is slowly transferred bit by bit back out into the universe. This is connected to what physicists call the Page curve, named after the physicist Don Page, who calculated in the 1990s what that curve should look like if information is preserved. Recent work involving something called islands, a new way of calculating the quantum geometry near the horizon that incorporates exotic regions of spacetime, has reproduced the correct Page curve, suggesting that information does escape without explicitly saying how. The mechanism is not yet understood, the details are genuinely open, but the direction the field is pointing cautiously is that the universe does keep its records after all. Somewhere in the Hawking radiation that leaks from a black hole over its incomprehensibly long life, encoded in correlations no human instrument could ever measure, is a complete description of everything that ever fell in. The history is preserved even when the object that held it is gone. It is worth sitting with that for a moment, even if it is just an idea in a room where you are resting. The universe forgets nothing. That is what the physics seems to be suggesting, even in its most alien and extreme regime. Even when matter crosses a horizon from which nothing returns, even when a black hole evaporates over 10 to the power of 100 years. Somewhere in the faint glow of a dying black hole, a complete record of what once existed is leaving the scene, just in a form that no one will ever be able to read. There is something both comforting and melancholy about that. I'll leave you to feel which. Now, let's go large. Because we have spent considerable time on the small end of the black hole family, the primordial ones, the mountain mass ones, the stellar mass ones, and it is time to move toward the other end of the scale. The end that is, in a word, extraordinary. Not all black holes form from dying stars, and not all black holes stay at the mass they started with. The most massive ones, the ones that squat at the centers of galaxies like great patient architects, are what we call supermassive black holes, and they are, by any human measure, incomprehensible. The one at the center of our own galaxy, Sagittarius A, which we gently visited earlier in our journey tonight, has a mass of about 4.3 million times the mass of the Sun, 4.3 million, and it is considered, in the world of supermassive black holes, relatively modest, quiet, well-behaved, eating very little. Others are far beyond that. The black hole known as TON 618, it's an unglamorous name, a catalogue designation, but it belongs to something genuinely astonishing, has a mass estimated at somewhere between 40 and 66 billion times the mass of the Sun. Not millions, billions. If you sat Sagittarius A next to TON 618, our galaxy's central black hole would be lost in the comparison, a small stone beside a mountain. TON 618's event horizons, the boundary of no return, the Schwarzschild radius, scaled up to its enormous mass, is so large that light itself, traveling at the fastest speed the universe allows, would take several days to cross from one side of the horizon to the other. Days. The event horizon of this single object is larger than our entire solar system. The whole extent of it, from the Sun out to the farthest known reaches of our planetary neighborhood, would fit inside this black hole's boundary with room to spare. It is difficult to form an image in the mind that is truly proportionate to that. Perhaps it helps to just note it and let it settle like a stone into still water. And TON 618 is not alone at these extremes. We know of others of similar or comparable mass. The universe, it turns out, has been producing these enormous objects since early in its history, and they have been growing ever since. How did they get so large? That question does not have a complete answer. The honest state of the science is that we are not sure how the first supermassive black holes formed, particularly those that appear to have been enormous very early in the universe's life, seen as blazing quasars when the universe was less than 1 billion years old. There are hypotheses perhaps they grew from a population of unusually heavy stellar black holes in the early universe, or perhaps some formed directly from the collapse of vast primordial gas clouds, skipping the star formation step altogether. Perhaps primordial black holes, the ones we discussed earlier, the ones hypothesized to have formed in the first fractions of a second after the Big Bang, seeded the process. We don't know, not fully. That honesty is important. What we do know is that supermassive black holes grow by feeding, by accreting gas, dust, and stars over cosmic timescales, and by merging with other black holes when their host galaxies collide. Every large galaxy we observe appears to have one of these at its center. Not most. Nearly every one. And that near universality is a clue that black holes and galaxies are not separate stories. They are the same story, told from two different vantage points. This is captured in what physicists call the M-sigma relation, sometimes called the Magorian relation, after the astronomer John Magorian, who first noticed it. The mass of a galaxy's central black hole tracks the speed at which stars in the galaxy's central bulge are moving, the velocity dispersion, sigma. The two quantities are tightly correlated. A big, fast-moving, energetic galaxy tends to have a proportionally larger central black hole. A smaller, quieter galaxy tends to have a smaller one. This tells us something profound. Black holes and galaxies did not form independently, with the black hole just happening to end up in the middle. They grew together, they shaped each other. The black hole regulates the galaxy. When it is actively feeding and blazing as a quasar, the energy and radiation it releases into the surrounding gas can blow material out of the galaxy, effectively putting the brakes on star formation. The galaxy in turn feeds the black hole material. They are in a relationship, and the universe as we see it, its galaxies, its structure, its distribution of stars across billions of light years, was sculpted partly by the behavior of the darkest objects at its centers. The darkest shaped the brightest. That is a kind of reframe that, once you sit with it, changes how the whole cosmos looks, and our own galaxy is not separate from this story. Roughly 4.5 billion years from now, which is, for perspective, about the same span as from the formation of the Earth to this present moment, the Milky Way and the Andromeda galaxy will collide. Andromeda is already approaching us, and the collision is not in doubt. It is in the math. When they merge, slowly, over hundreds of millions of years, the two spiral galaxies interpenetrating and swirling around each other in a vast gravitational waltz, their two central supermassive black holes will eventually find each other. They will spiral closer and closer, shedding energy into the surrounding stars and gas until they are orbiting each other in a tight binary. And then they will merge. When they do, they will release a burst of gravitational waves, a shout across the fabric of spacetime, unlike anything LIGO has ever detected. Far beyond what LIGO could detect, in fact, the frequency would be far too low for Earth-based instruments. Future space-based gravitational wave detectors, if they exist by then, might hear it, but no human will be there to listen. The sun will have long since exhausted its hydrogen, swelled into a red giant, and our part of the story will have ended by the time the two black holes at the centers of our merged galaxies finally touch. It is strange, and somehow quietly moving, to know that the ending of our galaxy's central pair is already written into the physics of the universe, timed for a date so far in the future that it might as well be eternity from where we sit tonight. But even that is not the end of the story we're telling. Because after the merger, after the galaxies have combined into a single vast elliptical, after the stars have shifted their orbits and the dust has settled across billions of years, the new combined black hole will just keep sitting there, waiting, growing faintly slower as fewer and fewer things come close enough to feed it. Cooling, in the Hawking sense, toward a temperature so cold it is essentially indistinguishable from zero, and so we begin to move now toward the real end point of the story. The thing the title promised, the end of time. Not of time itself, perhaps, but of everything that gives time anything to measure. The cosmologist Fred Adams and the physicist Gregory Laughlin laid out the framework most vividly in their 1997 book and accompanying paper, The 5 Ages of the Universe. They divided the entire history and future of the cosmos into 5 eras, each named for the dominant energy source of that epoch. We are currently in what they call the stelliferous era, the era of stars. The sky is full of them right now, or what looks like full at least, from where you're lying. Trillions upon trillions of nuclear furnaces, burning hydrogen into helium, helium into heavier elements, scattered across hundreds of billions of galaxies. The light from all of them fills the universe with a warm, bright haze. We live in the most luminous period the universe has ever had, or will have, but it won't last. Star formation depends on cold gas, and cold gas is being slowly used up. The Milky Way is still forming new stars, but at a fraction of its peak rate billions of years ago. Across the universe, star formation has been declining for about 10 billion years already. We are already in the long, slow evening of the stellar age. Somewhere around 10 to the power of 14 years from now, 100 trillion years, the last stars will go out. The smallest, faintest stars, the red dwarfs, burn their hydrogen so slowly and so efficiently that they will be the last to exhaust their fuel. But even they will eventually darken, and when the last red dwarf fades, the stelliferous era ends. No more stars. What comes next is the degenerate era in Adams and Laughlin's framework. A long, cold, dark age populated by stellar remnants, white dwarfs, neutron stars, and black holes drifting through space like embers, radiating away the last of their heat over vast timescales. The universe will be dark. No new light. Just the fading glow of objects that were once stars, cooling toward the ambient temperature of a cosmos that is itself cooling and expanding. And after the degenerate era, the black hole era. By this stage, matter itself has largely disintegrated. Protons may decay, in some theories they do, over timescales around 10 to the 33 to 10 to the 40 years. Even the white dwarfs and neutron stars will quantum tunnel into more stable configurations, their constituent particles slowly rearranging themselves over the astronomically long timescales that quantum mechanics permits in the fullness of time. The material universe as we understand it, made of atoms, made of protons and neutrons and electrons, will largely cease to be. And what remains? Black holes. They will be the last macroscopic structures in the universe. Not an asteroid, not a grain of dust, not a wandering proton, and just black holes spaced inconceivably far apart in an ever larger, ever colder cosmos, each one slowly, almost unimaginably slowly, leaking Hawking radiation into the dark. They will be the last beacons, the last concentrations of mass, the last ordered structures in a universe that has spent its entire history trending toward disorder, toward maximum entropy, toward the state physicists call heat death, where nothing can flow, nothing can move, nothing can happen because everything is the same temperature and there is no energy differential left to drive any process. In that universe, black holes will be the final holdouts, the last things with a meaningful difference between inside and outside, and even they are not forever. How long do they last? It depends, as everything does when it comes to black holes, on size. A stellar mass black hole, the kind that forms when a massive star collapses 10 or 20 or 30 solar masses, would take on the order of 10 to the 67 years to fully evaporate. That is a 1 followed by 67 zeros. Written out, it would take a long time just to count the zeros. The universe, at its current age of about 14 billion years, about 1.4 times 10 to the 10 years, hasn't even cleared the first digit of that number. We are, in terms of cosmic time, newborn. A black hole the mass of Sagittarius A, 4 million times the mass of the Sun, would take on the order of 10 to the 87 years. Some estimates run as high as 10 to the 100 years, or even beyond, for the largest supermassive black holes. TON 618, with its tens of billions of solar masses, would endure for a time scale that makes even those numbers look modest. These are not times, they are not durations that human intuition can meaningfully hold. They are symbols for an absence of structure in which almost nothing will happen, almost nothing can happen, for stretches that dwarf the current age of the universe the way the current age of the universe dwarfs the tick of a clock. And yet they will end. Even the largest black holes will eventually completely evaporate. As Hawking radiation continues, the black hole loses mass. As it loses mass, its temperature rises. Remember the great inversion: colder when large, hotter when small, temperature inversely proportional to mass. As the temperature rises, the rate of radiation increases, the process accelerates. It takes an almost incomprehensible amount of time for a large black hole to lose the first fraction of its mass. But once it has lost enough to become small, the end comes quickly. The final seconds of a black hole's life are not slow and patient. They are a burst, an explosion, a brief, intense flash of energy released as the last tiny remnant of the black hole evaporates in a final cascade of particles and gamma rays. And then, nothing. The black hole is gone. Not gone into something, not through a wormhole, not collapsed into a remnant object, not transformed, just gone. Mass converted to radiation, dispersed into the universe, adding a negligible warmth to a cosmos that has been cold beyond imagination for longer than the human mind can span. In 2023 and 2024, a group of researchers, Eino Falke, Michael Wondrak and Walter van Zwijlecom, revisited the calculation of how long these evaporation timescales last and found something interesting. By applying a Hawking-like mechanism to the curvature of space-time itself, rather than just to black holes specifically, they concluded that any massive object might slowly evaporate through a similar process. Not just black holes, white dwarfs, neutron stars, perhaps even ordinary matter. The universe's longest-lived objects, they suggested, might evaporate sooner than previously thought, revising the cosmic endpoint downward to something in the neighborhood of 10 to the 78 years, rather than the 10 to the 87 or 10 to the 100 that earlier estimates placed it. This work is recent, the field is still absorbing it, but the direction it points is consistent with the rest of the picture. Everything ends. The universe is extraordinarily patient with its endings, but it does not grant exemptions. So, here is what the last chapter of cosmic history looks like in outline. The stars have been dark for so long that the darkness itself is the oldest memory. The matter that once made planets and oceans and hands and eyes has long since tunneled into more stable configurations, or decayed, or drifted so far apart that the distances between particles are meaningless. The black holes, first the stellar mass ones, then the intermediate mass ones, then the supermassive behemoths, are the only things with shape, with mass, with an inside and an outside. They drift in the dark, spaced so far apart that if you could watch the universe from above, you would see only emptiness. A void so vast that even emptiness seems too small a word for it. And then, one by one, over a span of time that makes the current age of the universe seem like a single heartbeat in a life of geological epochs, they evaporate. Each ending in a brief flare. Each leaving behind a thinning haze of particles and radiation that disperses into the growing cold. When the last one goes, when the last black hole in the observable universe completes its final evaporation, whenever that is, whether at 10 to the 78 years or 10 to the 100, or somewhere in the vast uncertainty between, that is the last event. Not the last interesting event. The last event. There will be no structures left to change. No energy differences left to drive any process. The universe will have reached, or will be asymptotically approaching, its maximum entropy state. The dark era. Adam's and Laughlin's fifth and final age. A thin, cold, nearly featureless soup of stray photons, neutrinos, electrons and positrons drifting through a cosmos so vast and so empty that the chance of any two particles ever meeting again is effectively zero. Not silent exactly. Silence implies an absence that can be noticed, but nothing there to notice it. Whatever the final photon of Hawking radiation from the last black hole carries within it, whatever record of what once fell in whatever unreadable form quantum mechanics preserved it, will spread out into that cold, and it will not be read, and that will be that. There is a version of this ending that feels like grief, and I understand that. The stars gone, the planets gone, the black holes gone, and even the last faint thread of hawking light dispersed. Everything that was, gone. But there is another way to hold this, one that I find, at least on quiet nights, more generous. The universe did not have to be this complicated. It did not have to produce black holes at all, or stars, or planets cooling from molten rock into something that could hold an ocean. It did not have to produce the particular chain of events that led over 14 billion years and a nearly incomprehensible cascade of cause and effect to wherever you are tonight. Your room, your window, the sounds outside, the weight of your blanket. The universe ran that improbable chain, and here you are, in it. Every atom in your body was made in a star, not metaphorically, literally. The carbon in your cells, the calcium in your bones, the iron in your blood, these were forged in stellar cores and scattered by supernovae across the galaxy before this solar system even existed. You are not outside the cosmos observing it. You are a local arrangement of the cosmos observing itself, a brief, intricate, apparently improbable arrangement. And the black holes are not apart from this either. We spent the first part of tonight talking about how the darkest objects power the brightest light, how quasars, feeding supermassive black holes, blazed across the early universe when its chemistry was still forming. Those quasars seeded the structure of the cosmos. Their energy shaped when and where stars formed. Their feedback regulated the galaxies that became the homes of those stars. You live in a galaxy that was partly shaped by a black hole. The iron in your blood arrived here partly because of the environment that a supermassive black hole helped create. And Sagittarius A, the 4.3 million solar mass object sitting at the center of the Milky Way, the calmest eater in its current epoch. It has been there since the galaxy's early history, and it will be there long after every star in the galaxy has burned out, and long after every remnant has cooled, a lone patient object in the dark, leaking radiation so faint that it is colder than anything that will exist by then, until eventually, over time, scales with more zeros than this narration, has words. It too fades into the last echo of itself. We began tonight with the brightest object in the universe, a quasar J0529-4351, consuming a sun's worth of mass per day, shining with 500 trillion times the luminosity of our sun, blazing from a disk of heated matter 7 light-years across, the most luminous single object ever observed, a feeding black hole. And we arrive at the end of time with the last black holes, not feeding, not blazing, not doing anything that any instrument we could build would register. Just slowly, almost immeasurably, converting their mass into the faintest possible radiation and releasing it into a universe too cold and too empty to do anything with it. Brightest to darkest, hottest to coldest, most violent to most patient. The same objects, different eras, different sizes, different stages of an arc that began before our sun existed and will continue until the concept of after has almost nothing left to refer to.
And that arc, that single thread from the smallest possible primordial black hole that might have formed in the first fractions of a second after the Big Bang to the last supermassive remnant evaporating in the dark era, that arc is the story of black holes, not mostly black, not eternal, not dead ends, but the universe's most patient, most extreme, most enduring structures, the last things standing when everything else has long since returned to the formless dark.
There is something in that worth carrying into sleep. The universe is not running down toward nothing. It is running down toward something, toward a state of maximum stillness, maximum sameness, maximum entropy, yes, but it is doing so through an almost unimaginably rich history. through the ignition of the first stars, through the blazing of quasars in an infant cosmos, through the merging of galaxies and the collisions of black holes whose gravitational wave chirps are still crossing the universe right now, arriving at detectors built by the briefest of creatures on one quiet planet, through the photography of shadows by a telescope the size of the Earth, and half a ton of hard drives flown across oceans on airplanes, and a team of 200 scientists checking each other's math. Through all of it, we are not at the end of the story. We are in perhaps its most interesting chapter. The stelliferous era, the age of starlight, is still going. The universe is still forming stars, still building complexity, still doing the things that allowed something like you to exist and to wonder about any of this at all. And the black holes are here too, right now in this chapter. Not just the distant future's last remnants, but present and active. Sagittarius A is there, quiet and enormous, 27,000 light-years away. The quasar J0529-4351 is blazing, though its light takes so long to reach us that the universe has changed significantly since the light we see tonight left it. LIGO is listening. The Event Horizon Telescope team is analyzing data. Physicists are arguing, with genuine heat and productive disagreement, about whether the page curve tells us the information paradox is solved or merely sidestepped. The universe is not finished, and neither is our understanding of it. That is, I think, one of the things I love most about this particular subject. Black holes are not complete, they are not resolved. They are the intersection of everything we know best: general relativity, quantum mechanics, thermodynamics, and the place where all of those things most clearly break down and need to be replaced by something deeper. They are the universe pointing at its own incompleteness and saying, "There is still more here than you have learned to see." If you are still here, or still half here, wherever you are in the world tonight, thank you for spending this long, quiet night with me, wandering through it. I meant to cover the universe from the smallest black holes to the end of time, and I hope we did, more or less. We met primordial black holes so small that a mountain's worth of mass might be squeezed into the size of a proton. We met stellar black holes that form in seconds from the collapsing cores of dying stars. We learned that the black holes you want to be far away from are the small ones, the ones that would spaghettify you before you even reached the horizon, and that the ones you could technically fall into intact are the vast, supermassive ones, where the tidal forces at the horizon are gentle enough to allow an unharmed crossing right before the far more definitive harm that waits deeper inside. We learned that black holes are not holes and not mostly black and not eternal. We learned that the term was coined not by the physicist John Wheeler, but introduced by a science journalist named Anne Ewing in 1964, and that the old name was so unwieldy, gravitationally, completely collapsed object, that the replacement was a gift to everyone. We learn that the brightest kind of object in the universe is a feeding black hole, that J0529-4351 eats a sun per day and shines with 500 trillion times the luminosity of ours. We learned that Karl Schwarzschild solved Einstein's equations for a black hole from the Russian front of the First World War in 1916, a few months before he died of illness in those trenches, and that the solution bearing his name is still the one we use. We heard the chirp that LIGO detected on September 14, 2015, and marveled that two black holes merging 1.3 billion light-years away moved the arms of a detector by less than 1/10,000th the width of a proton, and that the merger itself converted 3 entire suns' worth of mass into pure energy in a fraction of a second, briefly outpowering all the stars in the observable universe combined. We looked at the photograph. The ring of light around the shadow of M87K's 6.5 billion solar masses, 55 million light-years away, captured by a telescope assembled from dishes on every continent, and flown home on airplanes in half a ton of hard drives, and we looked at Sagittarius A, our own galaxy's central black hole, so quiet in its current age that if it were a person eating, it would eat 1 grain of rice every million years. We followed Hawking radiation to the great inversion that black holes are colder when they are larger and smaller black holes are hotter, so that the very largest are colder than the cosmic microwave background and cannot yet evaporate. They are currently absorbing more from the ambient universe than they emit, and we followed the evaporation timescales out to their staggering ends, 10 to the 67 years for a stellar black hole, 10 to the 87 or beyond for a supermassive one, and possibly 10 to the 78 years by the recent and still debated revision of Falke, Vondrak, and Van Sylacom. And we arrived at the black hole era, at the dark era, at the moment so far beyond any human time scale that the numbers are purely symbolic, when the last black hole evaporates in a brief flare of particles and radiation, and the universe reaches a state of maximum entropy and the long story ends. I hope somewhere in all of that you found something that made the dark outside feel a little more populated, a little more interesting, a little more generous in its strangeness. I asked at the beginning of tonight where you were listening from. I still don't know, of course, but wherever you are, whatever city or countryside or corner of the world is quietly outside your window, whatever hour it is in your part of the night, you are somewhere in the stelliferous era, the age of starlight. The cosmos is still going, the stars are still burning. Sagittarius A is still sitting patiently at the center of the galaxy, ticking away its infinitesimal Hawking temperature, colder than anything that will exist when it finally dies. The universe is very large and very old and mostly very dark, but you are in it briefly, and that is extraordinary. If you enjoyed this slow drift through the cosmos and you would like more nights like this one, a gentle like or a subscribe really does help. Small creators like me rely on your support to keep these going, and it means more than I can quite say. And if you'd like to leave a note, wherever you are tonight, whatever time it is in your corner of the world, I would love to know. Until the next quiet night, stay as long as you like in Nightoria. Good night.